Hello everyone, this is Mr. Troha. Gonna have some astronomy notes. Not about, even though I got my Star Wars shirt on, not about the Death Star. It's actually about the death of a star. So we're gonna talk about the second half of life cycle of a star and what those are turning into. So just a reminder, as far as stars go, they're made up of hydrogen, helium, and they form into a nebula. The nebula gains the gases and it starts to compress. The gas clumps together, and eventually it clumps together to the point that we have high temperature, high pressure causes fusion. That creates the birth of a star. Fusion happens and it begins to emit that light, the light and the heat and the things that we think of that stars are exuding. So, important thing, and you've seen this, I've had this in multiple questions and videos. What causes a star to be the size it is? Well, it reaches this hydrostatic equilibrium. So this idea that gravity is holding everything in, but at the same time fusion is happening, explosions are happening as this gas pressure is trying to push it out. So the star is the size it is when those things are balanced. Now, of course, nothing lasts forever. Eventually, hydrogen starts to run out. When the hydrogen is running out, the fusion, amount of fusion, and the pressure pushing out starts to decrease. So when that happens, gravity starts winning, making the star collapse smaller and compress. Now, when it compresses, though, as it compresses, the pressure is trying to maintain, but that causes the temperature to go up. When the temperature goes up, it goes up high enough that now helium can start being fused. And as you fuse larger atoms, the amount of energy produced is greater. So helium fusion is hotter than hydrogen fusion. There's more outward pressure. And remember, mass has been decreasing through this time. So we have less mass, more outward pressure. So gravity is lower, outward pressure is bigger. You get a red giant. Now, how big, when we say red giant, how big is that? All right, here's a little slide. Notice this little yellow dot is going to be our sun currently. It's going to grow to 100 times the radius. So huge. In fact, how huge? When the sun becomes a red giant, it will be large enough to engulf the Earth. Okay, Mars would still be on the outside of it here, but it's going to take over the Earth. Don't worry, we should all be long gone by then. So, better to burn out or fade away? Well, the helium burning is done, and when helium's done, the star starts to collapse even more. It will start to fuse carbon, and if there's even more mass, then it's able to compress and create iron and have. And when right after that, it's a very short period of time, as Kung Fu Panda says, skadoosh, it's going to explode. We have, again, here's our life cycle of a star. We saw this in the last video. The top row is the main sequence, our average size stars. This is like our sun, 1 solar mass. It's going to become a red giant. It's going to kind of explode in a nova, planetary nebula, and be left with the core material as a white dwarf. On the lower end is massive stars. These are things 1.5 times or bigger than mass of our star. And so it's going to be a red supergiant supernova and then either become a neutron star or a black hole. So the core remnants, what's left of the gases and the things, the elements that are left from the star, depending on how much mass the star has, that will determine what it becomes. A white dwarf, somewhere between 0.08 and 1.4 solar masses. So we're talking about our sun is the number 1. That's 1 solar mass, so almost 1.5 times our solar mass. Now between about 1.5 and 3, that's a neutron star, and then anything from 3 and higher, typically between 3 and 10 solar masses, will become a black hole. So just some cool pictures of planetary nebulas. So let's talk about a white dwarf. White dwarf is it will collapse to about the size of the Earth. That'll be all of its stellar remnants, the compressed gases, the irons, the things that were fused at that point. No more fusion, but it does still release energy based on how hot it is, so thermal energy. Most stars will end up being white dwarf. Now, if you're more massive, so again, we said 1.5 times the mass of our sun or bigger, you will end up having a massive explosion we call a supernova. And during that time, you have lots of energy, and that's where elements bigger than iron can be fused together, and we get these heavier elements. Just a little visual here. Again, solar nebula becomes a star, goes through its sequence. In this case, a red supergiant will create a supernova, which is a black hole or a neutron star. And of course, all of that extra material that gets blown out becomes fuel for later stars. Here's some information about a neutron star. Again, it's between about 1.5 and 3 solar masses, and it collapses to about the size of a city. We talked about a white dwarf being about the size of the Earth. A neutron star collapses to about the size of a city. Well, how can it get so small? One, it has more mass, so you have more gravity pulling it in. But as it pulls in, these electrons and protons form together and become neutrons, which do not have the electrical forces holding them apart, which means they can cram together and become incredibly dense. Now, during that time, they also, in the collapse, cause the neutron star rotates. This ends up creating a couple of special types of neutron stars that you can read about at some point. There's a pulsar, which emits radiation pulses as it spins, as it rotates. And there's also a magnetar, which has an exceptional magnetic force. Just a little depiction. This is a picture of, this would be Vancouver, British Columbia, not Vancouver, Washington, but you can see to scale about the size of a neutron star. Now, the last one is about black holes. I'm not going to go a lot into this because we have a couple videos about black holes, but this is for if it has 3 solar masses or above. The gravity continues to pull it in. There isn't that outward pressure, and because the gravity is greater, it can pull it in even tighter. We're talking like a couple kilometers apart for something as much mass as 3 or more times the size of the sun. That gets compressed to about 3 kilometers. Now, when that happens, the massive amount of gravity in a single point causes space-time, which we aren't going to talk about here, but you can look up, it causes space-time to actually bend so much that the light cannot escape. So a couple of myths, or a primary myth about black holes. A black hole is not like this ginormous vacuum cleaner that as soon as a black hole is created, just sucks everything around it from, thousands of light years away. That's not true at all. In fact, gravity, which is the force that pulls things in, is dependent on mass. It's dependent on mass and distance. So if the amount of mass doesn't change, then the gravitational force isn't going to change either. So if our sun, even though it's too small, it just poof, became a black hole, the Earth would continue to orbit, all the planets would continue to orbit in the same way, not counting the explosion and all that. So they would orbit in the same way because it has the same mass at the same location, in the center of where the sun would be. So that's something that I think a lot of people think that everything just starts getting pulled in, and that really, you only see huge changes when you get close enough to the black hole. So otherwise, everything just orbits around. Of course, we wouldn't get any sunlight anymore, we wouldn't get any heat anymore, but we would keep orbiting around the same path. So just an overall summary story of the black holes. Something that people didn't know exist, but they thought that it did, and they eventually found it. But it's really strange because they didn't find it as we normally would with stars, where we get energy from them. We can see them with telescopes. They actually had to look at things that were happening around them. Stars that were orbiting a black hole, but didn't look like there was anything that was orbiting, or massive amounts of thermal energy in a certain location, even though there wasn't. There was kind of a blank spot there. So So they had to use some different techniques to figure it out. But what they did find out that black holes do exist. They find out that black holes have a humongous impact on galaxies. In fact, many galaxies have one large black hole at the center of them. Our own galaxy, the Milky Way galaxy, has a very big black hole. It's millions of solar masses in the center that everything's orbiting around. But even within galaxies, there can be millions of very small black holes. Something that's like this, a little bit bigger than our sun, 3 times the size of our sun, could create a small black hole, and those are happening all over the place. So just a little last minute refresher here. There are 3 things. The white dwarf, this is average stars. Most stars turn into white dwarfs. That's about the size of the Earth. A little bit larger, 1.5 to 3 solar masses, will become a neutron star, and then larger than 3 solar masses will become a black hole. Our next video is going to be on galaxies. We'll talk about those different things. Hope you enjoyed this. The death of a star.